This lecture will introduce some key concepts in probability and statistics that data scientists should know. Let's look at a histogram. We often find that real data is distributed around some mean with some tails. In many cases, there are good theoretical reasons to suspect that the shape of our distribution should follow a particular functional form. In fact, the central limit theorem, which we'll talk about in the workshop, tells us that many datasets will follow a bell-shaped or Gaussian curve, although other possibilities occur. The idea is that our data is a random sample from some underlying probability distribution, like the curve shown here, which gives the true probabilities. The histogram approximates the shape of this distribution, and by measuring quantities like the mean and the variance on samples, we can estimate the parameters of this hidden distribution. So in this case, we can see the probability of measuring a 0 is highest, and the probability of measuring a 3 is very low, and this is reflected in the sample we get. So this would represent a huge simplification. Instead of thousands of data points, we'd only need to know a handful of parameters which describe the true distribution. Furthermore, if we could say with confidence what distribution accounts for our dataset, this would give us some insight into the process by which our data was generated. So right from the start, let me mention that this is the so-called frequentist view of probability and statistics. There is an alternative, and these days a popular one, called Bayesian statistics, which is all about measuring confidence. We'll briefly discuss some Bayesian ideas in one video, but for now, let's be frequentists. So probability for us is therefore about the outcomes of experiments. We assume that outcomes are random, as in they can't be predicted exactly using Newton's laws or something like that. Often, there are only a finite number of possible outcomes, in which case probability theory is a lot simpler, and that's the case we'll mostly deal with. The classic example is flipping a coin. The possible outcomes are heads or tails. The set of all possible outcomes is called a sample space. It's usually denoted by the set notation of listing all of the possible outcomes inside of curly braces. For the coin flipping case, we have a set S with two elements, heads and tails. Another classic example in probability theory is rolling a standard die, in which case the sample space is the set containing the numbers 1, 2, 3, 4, 5, and 6. In probability theory, an event is a particular outcome or set of outcomes. In other words, it's a subset of the sample space. So for example, when tossing a coin, an event could be getting tails, or an event when rolling a die could be getting an even number, which would be the subset 2, 4, 6. Probability is a way of associating a number with every possible event. That is, it's a function mapping subsets from the sample space into numbers. So a probability function has to satisfy three properties. Formally, they are p of s is equal to 1. For any event e and s, p of e is greater than or equal to 0. And finally, if a and b are disjoint events, then the probability of the union of a and b is the sum of the probabilities of a and b. So let's break these down and translate them into English. The first rule says that the probability of getting any result is 1. This just means that something has to happen in the experiment, and fundamentally it means that the sample space contains all the possible outcomes. The second rule says that you can't have negative probabilities, although 0 is allowed for impossible events. The third rule is slightly more complicated. First, we need to define what a disjoint event is. Disjoint events are events, that is sets, which don't have any members in common. So for example, the sets 2, 4 and 1, 5 are both disjoint from each other. Next, we need a bit of set notation. The U is read as union or sometimes as or. So probability of A union B is sometimes read as the probability of A or B. And it's important to remember that this is logical or. So it means A or B or both. Therefore, the third rule of probability says that for events which are disjoint, to get the probability of one or both happening, we add the probabilities of the separate events. Hopefully this set diagram makes things clear. To interpret this, think of probability as equivalent to the area of the shapes, and the sample space S is the entire rectangle. To get the area of A or B, we simply add the areas of both circles. This is in contrast to this case, where the circles overlap, so they're not disjoint. In this case, adding the area of both circles overestimates the total area taken up in the sample space. To figure out what to do in this case, we need another bit of set notation. The probability of A and B happening simultaneously. This is written with an upside down U and read as A intersection B or A and B. So the Venn diagram is pretty clear, but just to spell it out, when the event A and the event B overlap, they have elements in common, so they're not disjoint. In this case, the probability of A or B happening is given by the equation probability of A union B is probability of A plus probability of B minus the probability of A intersection B. That is, we add the probabilities of A and B and subtract off the intersection to avoid double counting. The last thing we'll cover is the idea of conditional probability. This is the way to formalize the idea of the probability that A happened given that B already happened. So we have partial information about the event, and based on that partial information, we have to update our probabilities. So conditional probability is written with the bar, and probability of A bar B is read as the probability of A given B. so this probability can be expressed as the ratio of probabilities. To understand this formula, let's have another look at the Venn diagram. Knowing that B happened restricts the sample space from all of S, which is the whole box, down to just B, the orange circle. Then the probability of A in this smaller space is the number of ways A can occur in the space defined by B. Hopefully it's obvious that this space is just A intersection B. Related to conditional probability is the idea of independence. Independence is a crucial and often hidden assumption in many statistical and machine learning methods. The concept itself is fairly simple. Expressed mathematically, if the probability of A is equal to the probability of A given B, that means A and B are independent. This is just saying the fact that B happened has no effect on the probability of observing A. We could do some algebra to come up with a useful formula for calculating probabilities of independent events. Using the previous equation for conditional probability, when events A and B are independent, the probability of A is equal to the probability of A given B. We sub in the definition of conditional probability, and rearranging the terms, we find that the probability of A and B happening is given by the product of the probability of A and the probability of B. Basically, if A and B are independent, the probability of A and B happening is given by multiplying the individual probabilities.